Welcome to Quantum Photonics. This very interesting room today talks about the 3D reflector microchips, which could speed development of 6G wireless. Cornell University researchers have developed a semiconductor chip that will enable ever smaller devices to operate at the higher frequencies needed for the future of 6G communication technology. The next generation of wireless communication not only requires greater bandwidth at higher frequencies, it also needs a little extra time. The new chip adds a necessary time delay, so signals sent across multiple arrays can align at a single point in space without disintegrating. The team's paper, called Ultra Compact Quasi True Time Delay for Boosting Wireless Channel Capacity, was published on March 6th in Nature, and the lead author is our guest speaker here, Bala Govind, and I will be introducing him. Um, so, uh, Bal Govind is a third year PhD student in electrical engineering at Cornell University. He received his MS degrees in electrical engineering and mechanical engineering from North Carolina State University. He has worked with the RF Amplifiers Group at Texas Instruments in Dallas and on ultrasonic MEMS with the Advanced Technology Group at TDK in Vincennes in San Jose. His current research focuses on wave integrated circuit design with applications in communication and analog computation. He has peripheral interests in optics and quantum engineering. So we are very excited to bring you here our very special guest, Bal Govind. Bal, welcome to Quantum Photonics.
Thank you, Cecile. Um, so I guess I would get started. Um,
Yeah, the slides are
okay,
on the screen.
great, great. Okay, so let's get started. Okay, so thank you, Cecile, for the introduction, and thanks to everyone here for tuning in to this evening's presentation. It will be quite useful to refer to these slides pinned at the top here, so you can follow along as I try to explain our main ideas behind the work presented in the paper. So, today I'd like to talk to you about our solution to actually a decades old problem in wireless communication. As the title slide says, I will be discussing our recent work on a delay that makes wireless communication faster. So, you might be wondering how a delay could make anything faster. Well, you're just in luck today. Before diving in, I'd like to point you to a few links on this title slide from which you can access our full article published in Nature last month, as well as the nice coverage given by IEEE Spectrum magazine on the application of such chips to upcoming 6G technologies. I would also like to acknowledge my advisor, Alisa Apso, and Thomas Steppen, who is a postdoc in our lab, both of whom are co-authors on the paper that we wrote. So now on slide one, uh, I show you the motivation behind our work. It's actually very simple. What we're really just looking for are ways to give you faster data rate for cell phone communication or faster internet speed or other wireless communication modalities. Here, what I show is the evolution in data rates starting from 3G in the early 2000s, which barely had enough bandwidth to conveniently facilitate GPS on your cell phone. This soon evolved into the 4G technology towards the turn of the decade, wherein the speeds rose to accommodate very fast video buffering. This too, unfortunately, was insufficient to handle very high mobile traffic and in turn led to a conglomeration of a bunch of technologies that gave rise to now what we call 5G, whose main distinguishing feature is this buzzword called the Internet of Things, wherein various devices and appliances all talk to each other. Now, if I could just put that into context and to make it more clear as to what 5G from my perspective is, it would just basically consist of two technologies from engineer standpoint, that is a wireless engineer standpoint, and those are what's called the multiple input, multiple output scheme, which is a more of a system level thing, and the more hardware oriented approach called beamforming, which efficiently communicates information from mobile devices to cell towers and to other mobile devices. And that is, in fact, the technique that is the focus of this present work. So, on slide 2, I show you the main reason to pursue beamforming. So, it's simply to efficiently radiate microwave power from your cell phone to the cell tower, or the other way around, by transmitting pencil thin beams of this radiation. This is especially critical at higher frequencies, exceeding 6 gigahertz, uh, wherein the signal strength rapidly degrades through p-space propagation in the environment. Now, I will briefly review the problems that beamforming has faced so far and how we proposed to solve them. So, if you could please have a look at slide 3. In the upper half of this slide, I show the basic scheme of beamforming used in a typical array of radio receivers. Here, what we see is a wavefront that interacts with several antennas. Now, each of these antennas feed into a delay element that must add to or subtract some kind of phase or time delay so that the total signal from an array of these delay elements is a kind of coherent addition of signals that are all in phase with each other. And so when they add up together, basically, they would give a net gain to the received signal before it gets sent off to the subsequent microwave circuitry in your cell phone. Now, the beam profile uh, is characterized by what is known as the array factor, which is simply the sum of individual contributions of the delay elements in an array and applies to both transmitters and receivers. And this is the most important metric used in characterizing the fidelity of beamforming at higher frequencies. Unfortunately, this kind of coherent addition of signals in both time and space is actually quite hard to do across wide bandwidths, especially in an integrated circuit, that's a silicon chip, using current methods. And now I will explain why. The first method is to use what are known as phase shifters that only impart the same phase delay across all frequencies. Thereby, they can't impart the same time delay since higher frequencies would be delayed less in time than those lower frequencies. And the broadband signals components would end up at the wrong time or the wrong place, uh, which when these are processed by these phase shifters. This is exactly what we see in the first plot on the left in the bottom half of the slide, wherein even if you use a rather large array of 15 of these phase shifters, they actually misdirect different frequency components to different points in space, that is at wrong angles, and impart a squint to the beam. This ultimately distorts the information you're trying to transmit and lowers the effective data rate. The second state of the art method is called a true time delay circuit, which do actually delay all of the frequency components equally in time and solve this problem of misdirecting signals in space. That is, it solves the problem of what they call beam squint. The problem with these circuits, these time delay circuits, is that until now, these were designed as these gigantic, snaky transmission lines that induce delay. More on these later if time permits. The point is that very few of these true time delay circuits can be accommodated on a silicon chip, whose area is unfortunately determined by the maximum size that semiconductor foundry permits us designers to use. So, in effect, since only a few of these true time delay elements that were designed so far could be fit on a chip, the net array gain is actually quite small, as the figure in the middle shows. That is, the gain is less directive in the direction we'd like, which here is about 45 degrees that the beam is programmed to go to. So that kind of smudges out the signal also a bit. Now, our proposed solution solves both of these problems, as the last figure in the bottom right shows. Since it directs all the frequency components equally in space, and since a large number can be fit on chip, an array of such elements would give very directive array gain. Okay, so now that you have a background of what the first problem is, on slide 4, I quickly illustrate these points a little more graphically. So we again see the three methods in comparison. The phase shifter array on the right splits the beam into components, into its individual frequency components. and cause a squint. The true time delay elements are pretty good in that they form a directed beam, but are just too big. They're several wavelengths long and are too large to fit economically in arrays on a chip. And the solution that we propose, the very cute one that we will see presently, that is actually smaller, whose individual elements are actually smaller than phase shifters, and which mimic a true time delay in terms of frequency response. Okay, so lastly, before discussing the actual design of the chip, I show you the second problem that our device solves on slide 5. It turns out that the resolution of the delay that the elements induce is critical. Here on the left, I show you the 2D beam profile uh, for two arrays, one that has 10-bit high resolution phase shifters and one that has 2-bit low resolution phase shifters. We see that despite having a large number of elements in the array, low resolution phase shifters are pretty bad because they produce what are called spurious side lobes in the beam pattern. And these actually distort the transmitted image and increase the bit error rate. On the right, I show you the 3D beam pattern of these arrays again, wherein we see that a high resolution phase shifter actually has fewer side lobes and is very directed, while the low resolution phase shifter would send the image off in different directions through its side lobes. Okay, so now that we have the background of both problems, that is both beam squint and the resolution problem, on slide 6, I present a solution. Uh, and the chip that we came up with caused a delay that I first I came up with this term that I like to call a quasi true time delay. It's one that mimics a true time delay across a ultra wide bandwidth of about 10 gigahertz, and is very compact in its footprint. So it in fact is smaller than most of the state of the art phase shifters reported at this frequency range at least. As the figure shows, the chip could be inserted in the signal chain of a transmitter that forms one tile of an array. Here, the delay element can be placed before a cascade of a couple of amplifiers before radiating out the electromagnetic wave into the environment. I must say that this chip is indeed symmetric, and if you look closely, has several tiny squiggles and winding paths that cause tight delay, that cause delay in a very tight area, is what I mean. Uh, so I will now discuss the mechanism of how this chip functions. So if you could flip over to slide 7, I show you the concept of the quasi-true time delay. On the upper half of this slide, I show the main mechanism. The whole chip just consists of three main components connected together to form what is called a reflective type delay structure. Here we use a component that's called a quadrature coupler, or it's also sometimes called a hybrid coupler, or it's probably also called a Lange coupler, which actually is just analogous to a coupler that's used in optics, wherein a signal that's incident on an input port is just split off into two halves and directed at 90 degrees phase difference to two other ports called the through and the couple ports. They hit a reflector and they bounce back. They hit reflectors, that is, each half of the signal hits a reflector and bounces back. And these two components, when they bounce back, are finally add up at a fourth port called the output port. The point is that normally, so far in what people used to do was they used to make a reflector type phase shifting structure in which they would use a resonance structure that just causes a small phase shift. Here instead, we use a reflector, which is actually shaped like, which actually does the function of that musical instrument called a trombone. You know, the one whose length of whose cavity can be altered by programming the length of that thing. So the way we do it is by also altering the length of this trombone-like structure by digitally programming the length of tiny waveguides within this main structure. So the two halves of the signal would see obstructions in their path at lengths that you can program, and this causes a true time delay, and not only that, a programmable true time delay. So, uh, but how to make this thing compact? So to make the first component is of course the coupler. To make that compact, as I show on the top right of this slide, we simply overlapped two inductors, that's two coils with a couple of turns in them. built on two different metal layers and which are separated by the dielectric that the CMOS foundry provides. So to form this transformer-like structure. It's really quite simple and retains the right scattering parameters for over 15 gigahertz of bandwidth. Now on the lower half of this slide, I show you the structure of one of these reflectors, which by the way are identical. So this whole circuit is symmetric. So each of these reflectors consists of a series of fixed delay segments shown in yellow with options to engage smaller delay segments shown in blue. So these smaller segments are called sub-delay paths and they are tunable. That is, the length is variable. So for any combination of digital bit settings, it is the combination of several yellow fixed delay segments and one tunable blue segment that completes the return path for the signal to bounce off of. What I show what I show here is an example of what could be called a medium delay state. So here you would digitally program switches to disengage the first tunable delay line. You would then engage the second sub delay line with the delay line that you need. This completes the loop and the signal is shorted to the ground return path. The subsequent fixed and tunable segments are kind of irrelevant, although I would advise you to short them also to ground to ensure a strong return path to ground. On the right, that's at the bottom right of this slide, I show you the very nice 3D structure of the sub-delay path that we came up with. As you can see, it consists of a spiral waveguide that has switches at many intervals. These switches can be engaged based on how much delay along the waveguide's length you actually need. This is unlike other known true time delay approaches where you have these snaky lines running all over the chip and which are costly in terms of area. Now, on the next slide, that is slide 8, I show you in some detail the design of the sub-delay waveguide, that is this 3D reflector. The 3D exploded view that I copied from the last slide is shown on the left. The actual structure, when viewed from the top, that I used during the layout of the chip is shown in the middle, where I show you in full detail the actual transistors used in the 45 nanometer CMOS process that act as switches. Each switch taps off of this spiral, as you can see, and connects it to a common ground connection shown in this kind of greenish blue hue. Of course, when turned off, the switch doesn't really do anything, and the microwave signal just flies past it till it reaches a switch that does actually short the return path to ground. On the right, I show you the actual schematic of the cross section of the chip, wherein we only use the top three metals of the CMOS metal stack for the waveguides, since they are nearly lossless. We use the lower ones in the stack, that's the lower metal layers in the stack for routing digital signals, but we also connect many of these metal layers together with vias to form a low resistance ground return path. So now you have a full idea of the 3D structure of this reflective waveguide. On slide 9, for all your circuit nerds, I have an electrical model of the waveguides or transmission lines in microwave parlance. It is similar to a traveling wave structure with a number of smaller transmission lines strung together. That is, larger inductive segments are connected in series, and these can be tapped off with switches to access smaller transmission lines, which are also just cascades of more inductors, which can be connected to ground via another set of switches. So on slide 10, I put it all together and I show you the full structure of our delay element. As you can see, what we came up with is a system of waveguides within larger waveguide. And the whole thing makes a tunable length tube where its closed end can be moved farther or nearer away. And this acts as a reflector to cause true time delay. Okay, so there are two such structures inserted on the ports of the coupler to form a reflective type time delay, whose switches can be controlled with digital bits that control circuits called encoders and decoders that we also design by ourselves. And the outputs of those encoders and decoders actually are the actual control signals to individual switches in those waveguides. So now you're probably wondering how we actually measure the performance of this chip. So let us proceed to look at how we test the chip in the lab, and this is shown on slide 11. So on slide 11, I show you two simple setups to test this chip. Uh, so we microwave designers like to test how the circuits react to both small and large amplitude signals. A small signal test is shown on the right side and is used to measure the phase delay and the loss through this chip. We feed in the microwave signal through an RF probe and extract the output signal through another probe, and we measure the scattering parameters using a vector network analyzer. This is very similar to the way components in optics or acoustics are characterized also. On the left, what we have is a setup to measure the level of distortion of a high power microwave signal or, and how it would inflict any distortion, any nonlinearity on the circuit that we have here. What we do is combine closely spaced tones from two different RF signal sources and feed them into the circuit and measure the nonlinear mixing products, also called intermodulation distortion, on a spectrum analyzer. And we compare that to the actual tones that we injected in and which were phase delayed by the circuit. We found that our circuit is actually pretty linear and it takes about half a watt of microwave power to distort the signal going through it. Now, let us look at slide 12, which shows the measurements that we got. I've tried to divide the slide in two halves. In the left half, I show you the measured phase shift across the full band from 10 to 24 gigahertz and for over 150 states. What I really mean is the 150 combinations of digital bit settings that can control the switches in the transmission line. Immediately below that figure, I show you portions of the actual chip that must be activated to get those kind of delays. So what I'm trying to show you through the gradation in the color is the increasing delay that you would get as you activate farther portions of the reflective waveguides. That is, for example, if you wanted a small delay shown in light pink to red striations in the upper figure, what you would do is you would activate up to that correspondingly colored portion in the waveguide in the figure below. I hope that part is clear. Now, as we saw previously, uh, if we wanted even finer tuning, what you would need is to activate the smaller sub-delay waveguides associated with those larger fixed segments. I've tried to show you how that happens here in the right half of the slide. So what we see is a single spiral sub-delay waveguide that can be truncated at one of several points. You saw this previously through switches to terminate the waveguide's path to ground and to complete the return path. So basically, this gives smaller delays than the main waveguide and gives down to 1 degree of resolution. And this is actually some orders of magnitude higher than any of the previously reported digitally controlled phase shifters. Okay, note that I just used the term phase shifter pretty loosely here. While what I show here are actually variations in phase shift, if you look carefully at the phase variations in the upper left figure again, you would see that there is a gradual expansion in these phase curves. That is, the difference between the minimum and the maximum delays for each frequency is not constant. So it does not act as a pure phase shifter. But if we look closer, what we realize is that the full tuning range, that is the difference between the maximum and minimum delay, for a very high frequency, say 24 gigahertz, is actually double than that of a what you get for a low frequency, say about 12 gigahertz, which means that the net time delay is preserved across the band. And this is exactly what you want, as I mentioned previously, because this circuit can delay and transmit a broad range of frequencies equally in time, which prevents the beam squint and beam forming. And that, as we have seen, gives maximum array gain to the beam and would in turn boost the channel capacity and reduce the errors in the information transmitted. To put this more into context, please look at slide 13. I show here the measured time variations for a few representative states. So say, for example, you wanted 50 picoseconds of true time delay. What you would need is to build a device that gives a response shown by the green line. Instead, what modern phase arrays give you is what is shown by the dotted blue line, which unequally delays frequencies in time. Now, our device gives variations shown in those pink to brown lines. What we see is that for the desired true time delay of 50 picosecond, ours actually does pretty well, shown by the red curve. And we see that within a margin of about 3 picosecond, it covers frequencies all the way from 14 to 24 gigahertz. which is actually most of the communication and defense band in the US at least. This means that we've achieved characteristics uh, mimicking a true time delay within an ultra compact area that is even smaller than most space shifters. So, if you could please look at slide 14, I've tried to emphasize this last point again through the figure on the left. Here I compare our method, the quasi-true time delay, with other state-of-the-art techniques in silicon mostly, and in other exotic materials like phase change true time delay. Uh, what I show is that our circuit is much smaller than other circuits, only about zero point 0.3 millimeter square, which means that when packed in arrays in a silicon chip would boost the broadband gain of an array. Also, importantly, since the resolution is much sharper than other methods, by using these 3D spiral waveguides we made in commercial CMOS technology, it means that we wouldn't produce those spurious side lobes in the radiation pattern when transmitting from a user's cell phone. On the right, I show you the projected data rate, or in more technical jargon, the channel capacity, when we pack 16 elements in an array, which occupies only about 2 millimeters square of area in silicon by our calculation. We see that the variation in this channel capacity uh, depends on both the signal bandwidth and the signal to noise ratio. And the signal to noise ratio is actually determined by the environment. But ideally, assuming you transmit it on a relatively nice sunny day with not too many buildings in the way, you would, and you use all the bandwidth you could get close to about 40 gigabits a second with this kind of technology. These calculations are done with some basic information theory relating to channel capacity and incorporates effects of array gain and beam squint. And I would encourage you to look at the math in the methods section of our paper if you're interested in these details. Finally, on slide 15, I show you the main advantage our chip gives to the wireless communication industry. By comparing it with the two known methods I discussed through this presentation, we see that the phase shifters, while small, are limited in their ability to give large data rates because of beam squint and can't service a large bandwidth. True time delay elements can do that, however, but are too large to fit in arrays on a single chip, and the net channel capacity is thus limited. Our quasi-true time delay, however, achieves the best of both worlds for a huge bandwidth and thereby gives higher data rates. So to conclude, I summarize our design on slide 16. What we have made is a delay element that has a compact footprint in silicon, has a large bandwidth of over 10 gigahertz, has a very high delay resolution of 100 degree, very low loss through the circuit, comparable with state of the art, uh, is almost unaffected by a large within some reason it's unaffected by very large microwave power. And also, one point I hadn't mentioned earlier, also, since all we do is flip switches and we don't involve any active transistor circuits, it draws almost zero power from a mobile device when used in the signal chain for beamforming. So that's a major advantage also. Okay, so with that, I thank you for your attention, and I'm happy to answer any of your questions.
Yeah, thank you so much, Bal. And we'd like to announce to the audience that we are opening the floor for questions. Please raise your hand. If you have a question, we'll bring you up the stage. And just to reset the room, I'd like to reintroduce our guest speaker for those who just came in. Bala Govind is a third year PhD student in electrical engineering at Cornell University. He received his MS degrees in electrical engineering and mechanical engineering from North Carolina State University. He has worked with the RF Amplifiers Group at Texas Instruments in Dallas and on ultrasonic MEMS with the Advanced Technology Group at TDK InventSense at San Jose. His current research focuses on wave integrated circuit design with applications in communication and analog computation. His peripheral interests are in optics and quantum engineering. So yeah, we'd also like to welcome Hansen, our regular moderator here in Quantum Photonics, who came up the stage. And I think, yeah, I invited two of our other moderators on the audience now, Frank and Eric. Just feel free to come up the stage anytime. So Bal, I would just like to ask you about this. This is basically a proof of concept that you have now. So I had noted that
Maybe I'll ask a question when Cecile gives her mic. Oh, thank you for the presentation. I came in not too long ago, and the I'm complete. I don't know anything about this field. Completely, yeah, the um, beginner. So I want to ask a few very simple questions. Um, so the so to the device that you made, is it the waveguide basically adding on the length of the propagation and then reflect back maybe back and forth, but basically adding lengthening the optical path then so that the time of propagation is lengthened or delayed. Is that the idea?
Yep, that's exactly right. Yep. You basically just programmatically increase or delay the length of the waveguide, as you said. Um, and that's basically all the chip does, and it turns out to be very important and was pretty hard to do previously.
Got it. But this is basically a hardware uh, a solution, right? The and
Yep.
delaying. Okay. So the reason to delay the signal, is it because uh, the signals at different wavelengths propagating different at different speed, and then so originally in ideal situations you want the signal to say arrive at certain time or phase, design phase or time, but because of the propagation or the media propagation speed and depending on, let's say, for example, uh, wavelength or the frequency, they are physically delayed. Now that you want to delay the previously early arrival signals so that they align again. Is that the idea?
Yeah, that summarizes it. Actually, you said in a more sophisticated manner, but it's basically like you said, different signals of different wavelengths. I mean, we'd like them all to end up at the same point in space, because that would maximally use the bandwidth of the signal. And it just turns out that doing this in microwave hardware was harder previously. It was previously easier to just give the same phase shift to all of these frequency components, and not an actual time delay, but we managed to find a method to do that. So yeah.
Oh, I see. So actually, now that you're giving actually time delay, so to realign uh,
Yeah,
the signal. Okay.
yeah, yeah.
But I mean, I would think, I think, isn't that easier to do phase shift? I mean, I don't know how they originally did the phase shift, whether physical means or software, um, by software means. Is it, is it easier to do the phase shift or harder?
Oh yeah, so that's a great question. Yeah, you're right. This is not obvious, and actually, it requires digging through a bunch of very old literature. But it turns out that doing phase shift is much easier than doing a true time delay, because, like you said, to induce a true time delay, you would have to physically lengthen the propagation path. While doing a phase shift can be done in one of several ways. You can introduce a resonance at some point in the circuit and you could get a large phase shift. But that does not control the true time delay. That's the group velocity, as they say in the circuit, as in the way that you wanted to do it. And as you said, you could do this in software, and people do this. But usually that kind of thing is possible for low frequency signals, where your computing speed can keep up with that kind of digital phase shifting. But as you go to microwave frequencies like 10 or 20 gigahertz, that involves like very heavy computation to process in continuous time that kind of phase shift or time delay as you were talking about.
I see. Okay. So basically, it's at high frequency, it's faster.
Yeah,
The if you add in the computational, then it will actually depend on how fast you compute. Usually, probably is
yeah,
not as fast as. Okay, got it.
yeah. It's much better
Thank
to do
you.
it in an analog fashion than a digital computer.
Got it. Yeah.
Yeah, thank you, Hansen. And yeah, we have Vincent here on stage. I don't know if Vincent would like to speak now.
Still formulating the question.
So, Bal, I had noted, I think, in one article that, of course, you had mentioned that this problem has been there for a while, and you and another co-author tried to address this. What inspired you to work on this problem, and what challenges did you experience along the way when you were doing the experiment to come up with the paper? And how long did it take you before you got to the pre-publication stage?
Um, yeah, I would say the work. Okay, so to give a background to folks who do not have to deal with the vacancies of the semiconductor industry, so designing a chip and testing it and finally reporting results is in fact a very long process that is only partly within our control. So we designed the chip actually in the beginning of about I would say at the beginning of 2021, and then we waited for the chip to come back in about and came back in about January or February of 2023, and then we tested it and then we reported the results. But regarding the motivation behind this, so our lab, that's Alisa's lab, uh, has been investigating tunable transmission lines, or what they call tunable waveguides, for about the past 3 or 4 years, I would say. And we've been trying to repurpose this concept of tunable waveguides for various purposes like oscillators and amplifiers and those and all kind of microwave components. And then we thought we would experiment and see how this would perform in the context of a delay element. At the time we went into this, we were actually trying to build a phase shifter. Um, but then we quickly realized that this could actually produce a true time delay, and that's what the industry actually wanted. And so we fabricated the chip, and we got back the chip, and it turned out that our simulations kind of very closely matched the measured results that we got from the chip, and we thought that this could have some noticeable impact if other people copied our method and managed to shrink their own arrays of delay elements. So that inspired us to make it known to the broader community.
Thank you, Bal. So I'm quite curious about the scalability of this technology as we move towards the development of 6G communications and beyond. How easily can these miniaturized true time delay elements be integrated into larger systems or adapted to different frequency bands? Are there any limitations or challenges that you had discovered along your study that need to be addressed in scaling up in production?
Yeah, this is a great question. Actually, it's multi-layered. So the first one, I think, so I'll break down the question. So the question was, okay, I'll repeat the question. The question is about first scalability, and the second half was about challenges. So the first half, that's about the scalability. In theory, this does not face any uh, challenges in scalability. Why? Because it's implemented in CMOS process, and not even the most advanced CMOS process, actually a 45 nanometer node. So it's not the most advanced in that respect. So most design bureaus can access this process. So it's basically just a plug and play IP kind of block. You just take this and you then add to it amplifiers or digital signal processing with your existing CMOS circuits, and you're ready to just fab it. You could just take our layout, stick it in your existing SoC, the system on chip, and you can make your own radio transmitters and receiver arrays. And why it's scalable is because these are so tiny, which means they demand, and you can just dial them into tiny areas on in your existing layout, so it's not going to consume a lot of area. So yeah, it scales very well with respect to your the CMOS foundries, sorry, the CMOS design bureau's layout specifications. Now about challenges. This comes down to the kind of performance you would expect from different CMOS processes. So while CMOS processes are getting better and better every year, you have what are called silicon and insulator processes, in which the electromagnetic, the loss of the electromagnetic signal is actually kind of reduced because of the separation between the metal layers and the substrate and all that kind of stuff. Uh, what it comes down to is the performance of these transistor switches. So transistor switches are getting better every year, and they're able to switch faster and suffer less leakage loss. But of course, they could be better. And these are getting better as you go to smaller and smaller nodes, like say 28 nanometer or 16 nanometer or 4 nanometer or whatever. So that's where the designer would have to spend more time doing a more accurate simulation, a more uh, co-integrated design of both the electromagnetic structures and the digital circuitry. So yeah, so it's more of a design effort from a simulation standpoint, but I don't see fundamental limitations in terms of the technology used.
Yeah, thank you, Bal. So I'd like to invite anyone who would like to ask a question to come up the stage. And Hansen, if you'd like to speak, just flash your mic.
Yeah, so it's just a follow-up question. Actually, you kind of answered it when you mentioned the earlier when you mentioned the tunable waveguide. I was just about to ask the because of the size of the geometry of the waveguide would affect the wavelength that propagates it to it. I was about to ask whether you're just putting in lots of waveguides with different shapes and sizes and the to filter through the different frequency wave of different frequencies. But I suppose you say it's tunable. That means that you're maybe there's some kind of a sliding wall on the waveguide, and then you can kind of squeeze or expand the size and geometry of the waveguide. Is that the idea?
Yep, yeah, that's exactly it. Yeah, you could call it a sliding wall. You're just moving the obstruction to the wave, either nearer or farther away. So that gives you the kind of tunability. So I think you described that pretty well.
Cool, cool.
I have a question, Doctor. You're not consuming very much power, so I'm thinking that you're not generating much heat.
Yep, that's correct. Yep, we don't consume any power. We just program the switches like once. It just does the delay you want, and yeah, and it doesn't produce any heat. That's right.
Is the tuning the controller like piezoelectric?
So you're asking about the actual uh, tuning, like the circuitry, or the
Yeah, no,
display
I mean,
control?
what controls how do you, I suppose you have a control
Right. Okay.
on
Yeah.
the
Good question.
size of the wall and yeah.
Uh-huh. Yeah. Okay. So yeah. So I don't know. So if you could, I guess, look at slide 10, where I try to show the tuning. Um, basically what we do is we have an external microcontroller that could you could use any microcontroller. You could use an Arduino, you could use a whole full-blown FPGA, you could use an analog discovery, anything you like. Those feed in a few input signals, which we call an externally encoded bits thing. But these, of course, can't be too huge in number because we just do not have enough landing points to put wires on the chip to control every switch this way. So what we have on the chip is a way to decode these few bits into many, many more bits. So these are actually big digital circuits that we made on chip, and these are called thermometer decoders. That is, for example, if you wanted to activate the say the third segment on up to the third segment on the main waveguide and some part of the sub delay waveguide, you would leave the first two or three switches off in the main waveguide and short everything else to ground, and do a similar kind of action for the sub delay waveguide. And these digital circuits, which are a bunch of flip-flops and registers, they process the externally given bits and they convert them into the required signals, that's 0 or 1, to turn on or off these switches on the chip. Right. So that's how these switches are turned either hard on or turned hard off. And these control all of the switches within both of these waveguides and all of the sub-delay waveguides. So it's all digital control. There is no, and these switches are just transistor switches. These aren't piezoelectric or MEMS switches. These are just regular CMOS transistor switches. I
I
hope that
see.
answers that question.
Yeah, kind of, I mean, just, yeah, just one clarifying question. So the switches actually, but do they uh, physically kind of change the length of the wall of the waveguide?
Oh, you're asking. Okay. So what these switches do? So actually, this is a deep question. So you're asking why there even exists a reflection when you turn on a switch, right? So
Right. Yeah.
right. Okay. I was hoping someone would ask this. Okay. So um, in many wave mechanics, the way a reflection actually happens is there you have a medium and supposing you had two media that were one in
Right.
cascade
So,
with another.
okay. So
Yeah, so
maybe
there's an impedance
it's
mismatch. Yeah, right.
right. Yeah. So is that changing? Okay. Changing the media, the impedance,
That's
and
right. That's right. Right.
okay. But then so basically, well, yeah. I mean, actually, that's another question. So the wave, is it basically conducting in vacuum and then hit the solid media, or is it conducting in this mixture of vacuum and then solid media? I mean, you can, I mean, so long as there's a impedance or index refraction change, then you
Yep.
can weigh, you can reflect and then refract and change direction. But the uh, so the electromagnetic wave is traveling in the solid itself, or is it in vacuum?
Yeah. Okay. No. No. In the from a circuit's perspective, everything's just traveling on the surface of the wire or the waveguides. So you inject
Okay.
the signal into the circuit, it goes right through the waveguides, and then when it sees an impedance mismatch, when we say we short it to ground, what we're producing is like a zero impedance, which is actually a hard impedance mismatch to the conductive solid wire through which the wave was going. So then it bounces off of that junction where
Yeah.
you had the impedance mismatch. Yep,
Got
great
it. Got
question.
it. Okay. So basically, yeah, got it. So basically, the wave is in the solid media, and then you change the part of the part that in the path, that the impedance, and then you achieve that the change in length, right?
Yep, exactly.
Got it. Okay. Thank you.
Yes, so Bal, you mentioned that arrays of these new devices could achieve data rates of more than 33 gigabits per second. So probably you had already mentioned this in some of the slides, but I was off here for a while, so maybe my signal isn't good. But so I would like to ask, how does this compare to the current capabilities of wireless communication systems, and what potential impact could it have on future applications such as the Internet of Things or high definition video streaming?
Yes. Okay. So we project. Okay, maybe. Okay, I'm not an expert in predicting the trends of the semiconductor industry. But say, for example, we went all the way back to, I guess, slide one. Okay. So there, what I show in this from in the figure that I took from this reference. Um, it- we project a peak data rate of say 40 gigabits a second, which is much higher than the theoretical maximum of 5G technologies. And what that basically, and of course, there are many applications. Everyone loves higher internet speed, of course, for downloading movies and music and all that. But of course, the next wave of wireless communication is mostly done to serve AI and AI neuromorphic chips. And what that means is that you have several chips connected together, and each of them has some accelerator on it or any kind of other neuromorphic circuit. And then they have to transmit huge amounts of data to synchronize among themselves. And this is where this will play a major role because you're going to have this paradigm called on the edge computing, where there are going to be several radio nodes, and each of them comes with their own processors, and they all have to simultaneously coordinate and transmit large amounts of sensor data among each other. So the existing infrastructure is not really configured to handle this kind of information overload, and so it basically just comes down to the old problem of having more bits. So the more bits you can transmit, the better. And the way you do this is by transmitting over larger bandwidths. And if you have larger bandwidths over which you can synchronize signals at the right time and place, then you can achieve this kind of internet speed.
Yeah, thank you. So we have Kevin who just came up the stage. Welcome to the stage, Kevin.
Hi, yeah, the only thing I can think of is, and forgive me if you covered it, but like you talked about upscaling, but do you know if this will help the global, chip shortage, if it will affect it, or it'll be harder because of that, I guess?
Um, that's actually a hard question for me in particular to answer. But I could say that okay, I would give a rather naive answer. I would say in respect to chip shortage. I would assume that if you could pack more delay elements within a single chip, then your manufacturing cost actually reduces quite a bit. So you can build entire arrays of delay elements on a single chip instead of using multiple chips and having to wire them the way they do in cell phones right now. So I mean, I don't know, sound too optimistic, but it could solve a bit of that problem.
Oh, okay. Thanks a lot. A lot of research. Thanks for the homework.
Yeah.
Yeah, I was just thinking, of course, even if it will help solve the global chip shortage problem, I was just thinking about the initial investment in order to mass manufacture this chip. But of course, the outcome is, if the outcome would be favorable, then it's worth it. But yeah, I just was reminded of how humongous the job is and how it's expensive it is to manufacture new chips.
Right.
Along that line, what size wafers are you using?
Um, yeah, so the way I'm not too sure, but I think Global Foundry uses I think like 12-inch wafer for their 45 nanometer. Don't call me out on that. But basically, we run on a multi-project run. So we work with the university program. So they combine our design with several other designs, and they make that in a reticle that they arrange on a chip. on a wafer, and then there are several other products also riding along the same wafer. So everyone shares the cost of the wafer. So the design cost is actually quite low for us. In fact, free actually.
Yeah, Bob, I think there is a comment by Kyle here on the room chat. He
Uh,
is asking, yeah, but before you read this comment, I would just like to ask. He had made a reference here, and I don't know if, his reference. He should elaborate on it. So, Bob, would you like to read the question of Kyle on the room chat?
sure thing. Kyle asked whether this will speed up AI model capabilities.
Um, yeah, it probably depends on that. It, it, I mean, this isn't going to be directly applicable to AI models unless you find some way to do analog computing with this kind of a delay element. But probably increase the, I mean, the rate of communication between different edge sensors that probably have inbuilt AI accelerators on them.
Yes, so there was a reference posted here at the room chat. I hope that Kyle can come up and explain this a little bit because we are having some time constraints on reading this reference. I think this is a good paper also. So if you would care to explain or summarize the paper, please come up, Kyle. So, while we're waiting for Kyle to come up, I just want to ask also, that the potential extension of this strategy to optical and acoustic domains, I think it is intriguing. How do you envision applying similar principles to other technologies, and what new possibilities could emerge as a result? I'm curious about the broader implications of this research beyond just wireless communications. So, did you think about this?
Uh, so yes, we think about this every day in our lab, and actually, I guess you would have to wait for a couple of years for very interesting papers of this of these kind of tunable waveguides that we have to be published. And sure, there are other applications. You could use tunable waveguides for many kinds of analog computing tasks. Also, they use tunable waveguides in a more discrete fashion in interferometers and other radio astronomy equipment. Um, so those are potentially niche applications. Um, if you want to expand these kind of things to other domains like acoustics, I'm sure there are very similar analogs to making Helmholtz resonators with In fact, this is how Helmholtz resonators are actually built. They actually have a tube with where they cause impedance mismatch with the tunable length. So if you could do that, of course, people don't invest in on-chip acoustic resonators and metamaterials because the wide bandwidths are actually just relegated to speech bandwidth. But it could be an interesting academic pursuit if you want to use such 3D waveguides in an acoustic chip as well. It's not too difficult. About optics, I'm not too sure. I wouldn't commit to that, but I would assume that you could build delay lines the same way in silicon photonics. Unfortunately, silicon photonics do not actually support these many metal layers, and they don't actually use these kind of metal layers in the first place. But silicon waveguides could be routed around, but I'm not going to commit to saying that without a full EM simulation.
Yeah, thank you so much, Bal. So, we have Nas who just came on stage again. So, Nas, welcome. Welcome back.
Yeah, thank you. Quick question. The applications of the 3D for 6G, would that enable the transmissions of 3D images? Because that would be
Hmm.
truly breakthrough for medical or diagnostic if you would send. 3D images,
Yeah.
it would be unbelievably
So
helpful.
yeah, that's actually a very nice thought. So ultimately, it just comes to the amount of data you're sending, and the amount of data you're sending would in turn depend upon the bandwidth that you're going to send this much data in. So if you're going to send 3D images or holograms, of course, that's going to be very data hungry. You're going to have to transmit on several channels, I assume, uh, which is going to cover a large bandwidth. So if you can maximally use, say, 10 gigabytes of bandwidth to transmit your very detail intensive 3D image or hologram, for sure, this might help in that sphere as well.
And for space technology, it has many, many applications. If that's can be achievable, that would be truly a breakthrough. Imagine if you take a 3D images of
Uh-huh.
from space or a galaxy or from the brain. That would radicalize the way we do medicine and the way we even understand the space technology.
Yep. Yeah, sure. I think if you can manage to apply to use such high bandwidth transmission in those applications, yes, then it could make the job easier.
Yes, so I have a question from the audience which was sent to me. This question comes from Chato. Uh, she said, with the increasing demand for wireless connectivity in various applications, including communication, radar, and imaging, how do you envision the widespread adoption of these elements? And are there barriers and challenges that need to be addressed before they can be integrated, your work can be integrated into the mainstream systems?
Okay, that's actually a great question. So it kind of almost borders on the on the topic of legal jurisdiction of frequent and allocation of frequency bands, and many of our colleagues also talk about this. So what we propose is a way to maximally use bandwidth, which everybody wants, but it, there's the landscape of the frequency allocation changes in every country, and some countries allocate large bandwidth bands to some. I mean, some countries allocate bands between, say, for example, 28 to 32 gigahertz. That's like in the US, and and in Australia, they have something in a similar range between 28 and 40 gigahertz or something. So if you wanted to use this purely for communication, you would have to adhere to the rules of your own country. But there happen to be other applications like military radar or frequency hopping that use huge instantaneous bandwidths all the way from 10 to 18 gigahertz. So that's where, of course, this kind of thing would have maximal application. Um, Of course, when you go to a different country, they're going to allocate a different band. And say you wanted to, you could also use this for even higher frequency bands, say between 70 and 76 gigahertz or something, which is where the automotive radar band lives. Or if you could, or in better CMOS processes, you could extend this to what they call the D band. That's somewhere between 110 and to 140 gigahertz. That's 30 gigahertz of bandwidth. So if you could find a way to adopt this or design or just make a few tweaks or something to redesign this scheme in those frequency bands, it would be even more useful. You could get not just 10 gigahertz but 30 gigahertz of bandwidth. So yeah, so you could do radar or image processing or whatever at those frequencies as well.
Yeah, thank you. So there is another question from uh, Randall Linhart. He said, maybe you addressed this before, but probably you could elaborate a little bit. So Randall said, you mentioned that these QTTD elements are implemented in complementary metal or CMOS technology. Can you speak to the challenges or trade-offs involved in integrating such advanced components into the CMOS process, and he is particularly interested on how this affects manufacturing complexity and cost. So yeah, that's his comment and question.
Okay, yeah, that's a good question. Uh, yes, he's correct that this is implemented in a CMOS process. The thing is, CMOS is actually the yield rate, which basically corresponds to manufacturing complexity, is actually like the yield rate is very high in CMOS, which means that you mostly get back from the foundry exactly what you designed for because all the transistors, like lithography in CMOS processes, has been completely perfected. So now, unless you're really pushing the limits of the process in terms of speed or or let's say process corners or whatever, you don't expect to get bad performance from a commercial CMOS foundry. So, which is what actually encouraged us to design this in CMOS. Now, of course, people would look at the funky shape of this 3D spiral structure, but I would mention that such electromagnetic structures are not at all difficult to design. In fact, we have many colleagues who also try even crazier looking 3D structures. So it's not. So if you only use the design rule set that the foundry imposes on you, you're not going to incur any manufacturability problems. And all of our designs were made by strictly following the design rule guidelines of the foundry themselves, because they will enforce those regulations before you're allowed to send them the final mask set, the final artwork before they make the mask set. Now, would this be applicable to other processes? I'm not too sure about that because other processes aren't, such as gallium nitride or MEMS or whatever, aren't as mature in the production line as CMOS. So, and the main advantage of using CMOS is that it's very easy to integrate with every other circuit because every other circuit is most of, I would say 99% of circuits of chips floating around the planet are in CMOS. So I would say it's very easy to integrate with them.
I think George raised his hand, so I'm bringing him up the stage. And there is another question here from Bruno, but I'd like to address Dr. Young. George, hi, welcome to the stage. Would you like to speak?
No, I just want to say hello to everyone. I haven't joined the room for quite some time. I just got here. I probably prefer to listen a little bit more first before I can ask a question. Is that okay?
Yeah, sure. A long time no see, George. So welcome to Quantum Photonics.
Thanks,
And
everyone.
we, I
Yeah,
miss everybody.
yeah, missing everybody.
Yeah, all right. So we have a great speaker here with I think, I'm going to really follow the research of Bal here. It's very intriguing. There was another guest speaker whom we had who has been a recurring speaker because his research is also on chips and yeah, he has advanced so far. He's from UPenn. So Deep Jariwala. So anyway, the movement in terms of this research that on the field of BAL is quite exponential and there is a big demand. So please don't forget us, BAL, in the future if you get an award or you become a big billion-dollar founder. So there is a question from Bruno that I would like to read. I think he came in late and he left again, but he saw some of your slides. So he is saying Bruno said that he is intrigued by the reflective type phase shifting structure with 3D variable TTD reflectors. Could you provide more details on how this structure works and how it contributes to achieving ultra broadband phase tuning? It seems like a novel approach to him, but he is curious about the underlying principles. So sorry if you have to repeat some of what you said, but maybe Some members of our audience just came in, so thanks, Bal.
Okay, yeah, sure. So let's see. For those in the audience who would like a recap of how that works, uh, I would direct you to slide 7, I believe, which has the mechanism of the quasi-true time delay. Uh, so how this, uh, so he's right. The base structure is similar to what is called a reflective type phase shifter, except that we're not using it as a phase shifter here. We're using it as what is known as a reflective type phase delay, reflective type time delay. Here, the central component is the quadrature coupler. Uh, so it's similar to an optical coupler in that an input signal impinges on a port and is split up into two halves. Those two halves, as you can see in the figure, are directed at two other ports called the through port and the couple port. The signal goes to those ports and flows into waveguides inserted on those two ports and see an obstruction at some point within that waveguide and then bounce back off of that. So then they bounce off that and they come and then they add back at a different point called the output port. And that's where you would see the net effect of this element that you put in the path of the signal. So that's the basic mechanism. And as mentioned, it we've tried to squeeze the whole circuit within a tiny area. And unlike previous approaches, what distinguishes this one is that we've actually gone into the chip, that's in a 3D fashion, uh, down into the chip by using multiple metal layers. So that's a first. So e- e- even the coupler, as you can see on this on the right on the top right of the slide, is built on multiple metal layers. So we stacked metal layers. We made a transformer that is squeezed into just 890 by 90 micron size, and so that provides the power split. And then about the actual delay line, uh, the the fixed segments that you can see within this delay line, so those aren't tunable. Those yellow segments, they aren't tunable. But then each of those fixed delay segments can be either engaged or disengaged from smaller delay tunable waveguides. So those are the ones in blue, and those are these smaller tubes whose lengths can be made shorter or longer, and which provide the impedance mismatch, as we discussed in an answer to a question previously asked. So so it's very critical to make those delay structures very compact in size. So what we did was, instead of snaking those delay paths around the chip in a 2D fashion with wires, what we did is we went in a spiral and we went down into the chip, and we used a spiral that's built on three metal layers to build that sub delay waveguide, which can be tapped off at several points and connected to ground to give a variable time delay. So that is what, when engaged with the main delay line, the main fixed delay line, completes the return path and provides the interface at which the impedance mismatch happens. So the wave goes all the way there, bounces off of that, and then comes back and adds up with a similar copy of that bounced off of the other port, and the two of them add at the output port, which is where you would see the net time delay. I hope that clarifies the mechanism.
Yeah, thank you. Well, maybe he will send a question to me by email and I will forward it to you. And I think he will listen to the replay. So, yeah, thank you so much, Bal. So, I think I will be. Kevin, go ahead.
Oh yeah, I just have a quick comment, maybe off the top of my head. You know, do you think in the future this can be, made to be variable? More control with smart materials, and rather than just one rate.
Sorry, I couldn't get the last part. Did you say instead of just one segment, or what's that?
Oh yeah, if I got this correct, it's you have it. They're tunable, but when they're tuned, is can can you vary the rate, rather than just tune it and then, I mean, in real
Uh,
time,
I see. Yeah, that's a great question. That's a really great question. Okay, so what Kevin's actually asking is, instead of setting the all the bit settings just once and leaving it be, if you could tune them in time. So this is exactly the kind of thing you would need to do when you try to use it for radar, because when you use an array of these delay elements in radar, you would want to sweep the angle at which you direct the beam. So yes, you would have to programmatically change the bit settings that control uh, the length of the waveguides, and the that which in effect controls the beam, the direction at which the beam is fired off at every point in time. And of course, it depends on what the sweep time you want for the radar would be, so that your scan angle could be something like, say, 60 frame, let's say 120 degrees a minute, or maybe 120 degrees a second. It doesn't matter, but I would say that electronic beam scans, like mechanical beam scans, aren't too fast. But it depends on how fast you would like to raster your image, and so it comes down to how fast your bits can, your the switches can switch in time, and those, in fact, generally tend to do better with better CMOS processes and lower technology nodes, where your switches can turn on or off faster. So that's a great question, yeah, for in terms of how you would apply this to time varying applications.
Okay, thanks. Can I ask a question?
George.
Yeah. When you mentioned the multiple layer, so my first question is, when you talk about the chips, the current chips are only two-dimensional.
Yes, the current technique for most phase arrays or for true time delays. Okay, so actually this is a good question. Could you please see slide? Uh, it's actually uh, it's an extra slide on your PDF. That would be slide 19. So what I've shown here are what modern delay circuits are in terms of the way they are arranged. In a So what you can see over here on the left is what a phased array is, and on the right you see what a time delay element is, uh, according to the state of the art. What you can see over here is that these phase shifters have these tiny resonance structures like inductors. Those are snaked around in a 2D fashion. Now, the situation gets way worse if you're looking at the time delay element on the right, where you can see that these waveguides, from actually a rather recent paper, are actually arranged in a 2D fashion and go all around the chip to give you the kind of time delay. So, yeah, so far it's been quite hard to make them area efficient, and that's the problem we try to solve by making it go in a 3D fashion instead of in a 2D fashion, the way this chip, for example, has shown.
So how many layers do you think you can put them together as a 3D?
Yep, that's another good question. So, uh, okay, so to answer that question, it basically depends on how many metal layers in your CMOS stack uh, aren't terrible to propagate a microwave signal. In this process, that's this 45 nanometer CMOS process from Global Foundries, uh, it's typically the top three metal layers. Those are generally thicker and are qualified by the foundry to work with microwave signal routing. Uh, Now, if you wanted to go even lower and stack them all the way down to ground, it's theoretically possible. Like we could use all nine metal layers, but then as you go lower and lower, resistive loss uh, is going to eat up some part of the signal, and that may increase the insertion loss of the net time delay. And may cause additional resonances. But it's totally dependent on the kind of foundry, and I think future processors will support even more number of RF optimized metal layers. I hope that answers that.
Oh, very good. Thanks.
Yeah, thank you, George. And thank you, Bal. So we've been here for about an hour and 1.5 hours. So I'd like to ask Bal how much more time does he have for us?
Um, I can stay for about 15-20 minutes. So as you ask more questions.
Yeah, well, I think there are one or two questions on my side, and I just saw Ihab who came up on stage just now, and I'd like to welcome Ihab. Hello, Ihab.
Hello, guys. How you doing? Long time. It looks like
Yes,
an awesome paper. I cannot finish it right now. I'm just reading. Awesome paper. I'm looking at paper right now.
yeah. So you're going to ask a question later on, or you would just like to say hello?
Yes, both.
Okay. So I will just read one of the questions that was sent to me. Yeah, I hope some of the questions are not very redundant for a speaker here. So, there is a question from Edna. She is asking, precision in fabrication is indeed vital, especially when dealing with sub-wavelength features. I'm also interested in the materials used for these components. Are there any specific material properties that are essential for achieving the desired performance, such as dielectric constant or thermal conductivity?
Yeah, okay. That actually is an important consideration when designing these. Um, so luckily, our task as designers is actually made considerably easier with the electromagnetic simulation software. Uh, so those materials that go into building the CMOS are have, like you said, dielectric constants, thermal conductivity, resistance, whatever. So those are uh, imported and stuck into equations into the electromagnetic solver, and the solver tells us via 3D electromagnetic simulations if the signal will completely die or probably get or will actually come out of the chip without being distorted too much. Uh, Typically, in CMOS process, the metals are usually made of copper or aluminum. Those are the ones that we use for making waveguides or routing digital signals. And the actual dielectric that that we're talking about is usually silicon dioxide, sometimes hafnium dioxide. Uh, but those have a dielectric constant, I think, of like somewhere, so it's in the range of like about 2 to 4. So, what the real effect of that does is when you overlap a two pieces of metal, that's say on the top two metals of the stack, it induces a capacitance between those things, and that's where you get this distributed inductor capacitor kind of structure, and that is what causes artificial transmission line type of behavior, which gives you this true time delay. So yes, we all of these material properties are implicitly taken care of in the circuit simulation software, and luckily we do not have to do that by hand, but very important to consider.
Yeah, thank you, Bal. So we have Alex who just came on stage, and I'd like to welcome Alex. Alex, welcome, and please feel free to unmic if you have a question.
Yes, thank you, Cecile. Very good to see you again. It's been a long time. Thank you, Bal. Very interesting work. I'm interested in advancing this or applying this kind of technology towards the t- terahertz and optical part of the spectrum. I did see that you went up to 30 gigahertz in your work. What would be the limits to use this approach in silicon with CMOS? And what other materials you would consider if you want to exceed these limits?
Okay, that's a very futuristic question. Yeah. So the process we went for, like you said, is a commercial CMOS process, whose properties are very well characterized and whose performance in typical circuits is guaranteed by the CMOS foundry to work till about 60, 70 gigahertz without a hitch. Uh, but as you said, if you wanted to extend this to terahertz or even something like say 300 gigahertz or whatever, uh, typical CMOS processes aren't optimized to do that because they are the devices' cutoff frequencies. That is the cutoff frequency for the transistors. It's in that high. Now people have tried to circumvent that in certain by using very complex circuit tricks, but the easiest way is just to look into the research and find a material that can actually make, in which you can make transistors that work that high. And there have been several processes where, such as indium phosphide, which actually have transistors that work up to, like, say, 600, 700 gigahertz, which is just shy of the terahertz regime. So if you could actually build uh, good switches, and you possibly can at those frequencies with such processes like indium phosphide, you could definitely hit the terahertz regime. Of course, the problem is you'd have to make the process mature enough to support many metal layers of which are qualified for microwave transmission to like curl up a 3D waveguide in that process. But assuming you had good transistors and those processes in maybe like 5 to 10 years actually do support many RF metal layers, sure, you could possibly extend this approach to that also.
Yeah.
That's great.
So,
Thank you.
yeah. Sorry, Alex. I think there's a bit of latency in the app, so we are not like maybe communicating in real time. So there is a question here. Last question that was sent to me from Reno. He said that he's wondering about the thermal management of these devices because with increased integration and miniaturization, how do you prevent overheating and ensure efficient heat dissipation, especially in high power applications?
Oh, okay. This is okay. This is more of a mechanical engineering problem, I guess. Uh, with respect to this circuit, I'm glad to say since it does not consume DC power, there is not much of a problem of heat dissipation because there are no active amplifier elements. But then, uh, but then the question was what you would do in high power. Now, there is always now if you inject high power into the circuit because of some resistive losses, there could be kind of some kind of heat generation, and some heat could get dissipated. Or, for example, if you cascaded the delay element with a high power amplifier, of course there will be heat dissipation. But then the way the semiconductor industry tries to handle this is through better packaging. And I don't mean putting a big fan on a heat sink, which is what people do, and it's worked. So you put a big heat sink and a fan under the chip, and it just takes care of heat dissipation. But what they do is these days, they when you try to integrate chips like this in a package with digital circuits, they have interconnects, uh, which basically this is a whole field of research, and I'm not an expert in this, but I'm aware of ways and means by which they have what are called thermal interconnects to an external package, uh, which is made of a different material, which rapidly sucks up the heat through very thick copper pillars from this chip, on which you have high power microwave signals flowing, and transfer that heat off to another chip where the where the cooling takes place. It's an interesting field.
Yeah, thank you, Bal. So, on my side, I don't have much questions. Of course, we will reflect and listen to the recording that we have. And I'd like to ask Ihab if he is now ready to speak, because if not, then we will prepare to wrap up.
No, I'm good. Thank you. I don't have enough time to go through the. Although I love the frequency modulation and reading through it, but the next time. Thank you.
Yeah, thank you, Ihab. So, we have Darcel here on stage, and he will help us do the countdown in a while. And I would like to take this opportunity to thank Bal, who had enlightened us so much about his work and has given us hope about what's happening in the discoveries and innovation, because I think the paper that he has is quite really outstanding. So, it is our future. So, Bal, thank you so much for joining us. We hope that we can invite you here again in Quantum Photonics. Our speakers are recurring speakers. In fact, I think this month we have two speakers who requested us to have rooms for them because they have a new paper. So please don't hesitate to get in touch with us again if you feel like you wanted to discuss your new paper or any topic from your lab. Thank you so much. We really appreciate your presentation. So, do you have some last message for us before we close the room?
Thank you, everyone, for finding our paper and our research and our approach interesting. I will say, for sure, I will, if all goes well, I would say stay tuned for more awesome reflectors. We have many more ideas, and I would be happy to present again in the near future.
Yeah, thank you. Please know that the people of Quantum Photonics are rooting for you and your future success. So, yeah, please let us try to tap our mic, flash our mics for our guest speaker, Bal.
Thanks for listening. It was great.
Yeah,
Okay,
so that's how we upload you, Bal, in Clubhouse. So, yeah, thank you so much. And I would like to ask Bob if he has something to say. Otherwise, we will pass on the mic to Darcel to help us close the room by a countdown.
Well, I think
Yeah, all right. So, people in the audience, I could not say all of your names. Thank you so much for your support. That's why we are still here in Clubhouse. So, I'd like to pass the mic to Darcel now to help us close the room.
Thank you, Cecile. And Doctor, thank you for a great talk. To close the room, we're going to start our countdown from lucky number 8. Is everybody ready?
Ready?
we,
8,
Ocho,
Ocho.
Alex 7,
Siete.
7,
Dr. Yang 6,
Six.
Kevin 5,
Fiverr.
Vincent 4,
Cuatro.
Bob 3,
3 it is.
Cecile Dos Equis.
Dos Equis.
Good doctor, you're number 1. Would you call out our last number, please?
one.
Number.
Yeah, thank you
No,
so much, Bal, and yeah,
thank you,
felicitations for your work. See you
thank you
back in
very much.
Quantum Photonics soon, and good night, everyone. See you in the next rooms.
Thank you. Good night, everyone.
Bye.